Thank you for introduction. I'm Manami Sunako in NHK Spring, Japanese company. And we produce some kinds of automobile parts and suspension and seat and so on. And so today I will talk about the influence of microstructure on hydrogen wave and about high strength spring steel. Suspension springs have been required to be lightweight to reduce CO2 emissions. Springs use high-strength magnetic steel with tensile strength of 2,000 megapascals. And the problem of the spring is hydrogen treatment due to corrosion. One of the ways to improve hydrogen treatment resistance is hydrogen trapping and dislocation binning by fine carbides. We focus on the emission carbide in this study. It is known that when sequence are added in steels, the carbides finally precipitated within grains. Sequence said to delay the transformation which on carbide to cement type. Recently, it has been reported that the epsilon carbide may have hydrogen trapping ability. And additionally, the carbides have been refined to be by rapid tempering. Therefore, we focus on the requirement of epsilon carbide by combining silicon addition and rapid tempering. On the other hand, it has also been reported that the amount of retained austenite increases when silicon is added and rapid tempering is performed. The method of retained austenite to hydrogen treatment includes improvement in its property due to solution trapping of hydrogen or deterioration due to deformation-induced magnetic transformation. And therefore, the objective of this study is to investigate the influence of the size and volume of carbides and retained austenite on hydrogen treatment property about the rapid tempered high silicon spring steel. Now I explain the experimental method. Two types of spring steels with different silicon content were used. Treatment is shown here. In order to eliminate the grain size differences, induction heating IH was used for wedging, and IH and harness heating FH were used for tempering. The specimens were three types of steels with different silicon content and tempering speed. Although the grain size and hardness was the same, but the sharp impact value tended to be highest for two silicon IH steel. In order to evaluate the hydrogen treatment properties, a 4-point bending test was conducted under cyclic corrosion test. The fracture life was measured by detecting the electrical signal output when the specimen fractured. And the cathodic hydrogen charging test was also conducted and without fractured surface. The size and volume of carbides retained austenite were measured using 10 sacks, synchronous radiation study, replica method, and ES. I will move on to the result. This is the result of hydrogen weight property of each specimen. It was found that two silicon IH steel has the longest fracture life. At the same tempering rate, high silicon steel has a longer fracture life than low silicon steel. At the same amount of silicon added, IH tempering increased the fracture life by 2 to 10 times than FH tempering. And 2-3-point steel fracture in a short time. Therefore, it was expected that there would be a large difference in microstructure compared to AH tempered steels. These are the fracture surface of this specimen. It was found that the original fracture was for IH tempered steel was inclusion or flat facet. Previous research in the case of endorsement bearing steels, the flat facet is said to be 1 to 3 plane of mountain side, which is formed by endorsement, transforming into deformation into mountain side. I explained the flat facet in detail in discussion part. On the other hand, the original fracture for 2-silicon FH steel was inclusion, was not flat facet but inclusion. And the more the fracture life longer, the more the intragranular fracture occurs. Next, I will explain the characteristics of the end-austenite and carbides. It was found that IH tempered steel contained more retained austenite than FH tempered steel. Among IH tempered steels, the highest amount of silicon, the highest amount of retained austenite, which is consistent with previous research. This is the result of size and volume of original carbide. This is a figure. This picture shows the carbides in 2-silicon IH steel. The most of carbides were the epsilon carbide, not cementite. The morphology of epsilon carbide was mostly light, but some spectral carbides were also that. The forms of epsilon carbide was the same in all specimens. This figure shows the relationship between size and cumulative volume of epsilon carbide. As you can see, the silicon still had a high volume fraction of fine carbides. And this figure shows the average volume of fraction of epsilon carbide. 1.4 silicon IH still had the least amount of carbides. And on the other hand, the carbides volume fraction 2-3.8 and 2-3.8 still was found to be equivalent. We also observed the distribution of carbides for 2-3.8 and FH steel with replica method. In 2-3.8 steel, there were some white areas where the carbides did not participate much. This is thought to be a retained austenite. On the other hand, when looking at the areas except the retained austenite, and many carbides appear to be uniformly distributed within the dust. On the other hand, 2-3.8 steel, there had less retained austenite, but the lash shape can be seen clearly. In other words, there are many lashes where the carbides did not precipitate much. We consider how the carbides and retained austenite affect on hydrogen embrittlement. I will explain the carbides. And Hesse theory assumed that poison and annihilation of dislocation and hydrogen trapping in vacancy, resulting in vacancy aggregation and fracture. So it is important to suppress the dislocation motion in order to prevent the hydrogen embrittlement. And the resistance to dislocation movement is expressed by Ullmann's equation, and the amount of precipitation strengthening increases as the carbide distance decreases. This figure shows the distribution of carbides over each specimen. 2-3 point still has a large amount of powers, uniform, which is uniformly distributed within the Earth. In contrast, 1.3 point still carbide volume was small. 2-3 point which still has many lattices with low carbide density. Therefore, we expected that in 2-3 points, if dislocation motion and vacancy formation were suppressed the most. And next, I explain the effect of the austenite on hydrogen embrittlement. We thought the origin fracture of IH tempered steels were wrapped facet. This is a previous research. There is a wrapped phase in the original fracture, which exhibit 1-3 plane on the content side. The authors assumed that the stress was applied to the specimen, again, those austenite waves become the more significant with the mountain side, and resulting in deformation in mountain transformation. The mountain side are highly sensitive to hydrogen embrittlement, so becoming in the origin fracture. In this way, we thought that within the austenite was the fracture line. Finally, we summarize the hydrogen embrittlement mechanism about the level extent on high silicon steel. 2-3 steel, which have the longest fracture life, contains many retained austenite. Retained austenite was considered to be the origin of fracture. On the other hand, many carbons within the Earth suppress dislocation movement and ground growth. In contrast, other two steels have less retained austenite, but dislocation in the hydrogen is removed and concentrated at the grain boundaries. In this study, the suppression of growth by carbides had a greater contribution to the fracture line than crack initiation due to retained austenite. These are the conclusion, and thank you for your attention.